Welcome everyone to this first episode of SYCL Session series. Try saying that after a few drinks, where we'll do a roundup of the latest SYCL projects, some papers, events, and alongside that we're going to have a talk by our guest, Vincent Pascuzzi. My name's Rod Burns, I work at CodePlay. I've been working and supporting SYCL developers for a few years. I'm a strong advocate for the use of open standards in HPC. CodePlay, the company I'm at, we work on more than one SYCL implementation, and we've enabled SYCL on lots of different hardware. And with me, I've got Tom Deakin. Do you want to tell us a bit about yourself?
Yeah, I'm Dr. Tom Deakin, and I'm from the University of Bristol. I'm a lecturer in advanced computer systems there, mainly interested in researching performance portability, how to get HPC applications running at massive scale across a wide variety of HPC architectures. So part of this is helping with SYCL, as that's one way that we can enable performance portability across different platforms. It's this, as you all know, this parallel programming model based in C++, standards-based, looked after by Kronos. And it's been very interesting to see how it's developed since it was first released quite a long while ago now. Was it, when was the very first version of SYCL? About 2014, I think?
Yeah, I think that sounds about right, yes. It's probably changed quite a lot since then.
Yeah, so for those listening far in the future, we're now in 2022, so we've all been looking at SYCL and been involved in the ecosystem for 8 years now, I guess.
Yeah. I guess this talk as well, given your background, performance portability and stuff, could be interesting too, because I think Vincent's involved in some of those, I guess, measuring that and trying to figure that stuff out for some of the labs.
Yeah, I'm really looking forward to hearing Vincent's talk that you'll hear a bit later on.
Yeah, excellent. So at the end of last year, Tom and I started talking, and we thought we'd start a kind of regular little show, or whatever you want to call it, just to talk about what's happening in the SYCL community, and try to bring along a guest speaker along with that. And I suppose before we jump into that, I just want to remind everyone that if you want to find out about the latest SYCL news, blogs, videos, and events and stuff like that, the place to go is sycl.tech. And also, if you're getting started with SYCL, then if you go to sycl.tech/learn, there's links to lots of different resources that can get you up and running, and tell you about all the different implementations and resources that are available, and stuff like that. So I thought we could start off maybe talking about some of the highlights from the last couple of months. I'm the sort of person that keeps an eye on kind of GitHub and sees what kind of open source projects that are happening that are using SYCL. And I've noticed a few recently that I suppose are quite relevant to, I think, what Vincent's going to be talking about later. So the researchers at CERN, which is in Europe, and they work on experiments with the Large Hadron Collider. So they have lots of data to process and work with, and they run a lot of different simulations. And there have been some interesting talks in the past from them about how they're looking at ways to migrate from kind of CPU-only systems to GPUs. And I noticed a few different projects that have been happening in that space of experimenting with SYCL and trying to get more generic algorithms available for some of those things. And there's someone called Attila Krasnahorki, if I pronounce that correctly. He's been working on recently some shared algorithm plugins that are good, that are used by kind of different experiments. There's one called Track, which is looking at different accelerator types and basically how to run a chain of algorithms. So we'll make some of the links to those available through the text of the video as well on this thing. I think one of the things that I was going to talk about, which is maybe blow my own trumpet a bit, but talking about some of the work my own colleagues have been doing recently. So end of last year, we released a demonstration package which includes SYCL support with a RISC-V simulator target. This was done in part as a project that was working with a project in Japan. We've taken that a bit beyond that with the research team. They've developed a sort of full software stack showing a deep learning application running on what's called the SPIKE simulator, which is a RISC-V simulator, which is running with the ResNet 50 model, doing inference on images. So could be interesting for people who are interested in RISC-V. Again, we can put a link to that in the description if anybody wants to try that out. And we're hoping to see some real hardware coming soon as well. I don't know what you think about RISC-V, Tom, if you've got any knowledge in that area in terms of your performance portability.
Yeah, we're just starting to think about RISC-V. It's interesting. It's an interesting architecture. I think we're all keen to see some real implementations and to see what this hardware looks like, as you mentioned, that we're hoping to see some soon, and we're keen to see what that actually looks like. I think it's been really interesting to hear that you've been porting and providing a SYCL implementation that targets the RISC-V architecture. I think the breadth of SYCL implementations that we've seen over the last little while has definitely sort of exploded, and there is a huge coverage of the types of devices, the types of architectures that one or more different SYCL implementations are trying to support. The more we can support, the better, really. So yeah, it's really cool.
Definitely. So in the research community, there's been a few things that have been happening. I think one of the ones that I noticed was published from HPC Asia, which I think it was a Japanese event, but obviously held virtually this year. And the paper was called Multi-Hetero Acceleration by GPU and FPGA for Astrophysics Simulation on one API. And I guess the purpose of it was to investigate use of FPGAs alongside GPUs and looking at the performance of some astrophysics code. And from the results of that, it's very positive, actually. I haven't really seen any research using FPGAs alongside GPUs, certainly in that way with SYCL. I was kind of interested to see that. I don't know if you have done much with FPGAs as well, Tom, or...
No, not much personally, but I do see that they have a lot of value, and we're seeing that processor vendors are now sort of expanding their offering. You know, if you take Intel, for example, they're offering CPUs and GPUs and FPGAs. And there's obviously the acquisition of Xilinx 2 by AMD that's currently in progress. So we're seeing this, processor vendors thinking in kind of a general way of providing different types of compute resource. And obviously you have to program them all somehow. And then obviously once you can program them, you really want to start thinking about how you can best use them for your applications. And obviously astrophysics simulations are really important part of science, and obviously very complicated. So yeah, I'd be really interested to read that paper and see what they were thinking.
Yeah. I mean, I had a quick scan through the paper, and I guess it was interesting to see there's no meaningful performance difference between the kind of CUDA plus OpenCL and the SYCL implementation to that. But again, it's a good tick box for performance portability, and nice to see that. But yeah, again, we'll put a link to that paper so people can take a look at that too.
Yeah, great. It's interesting. It's nice to see some of those comparisons with other different programming models to see how things are going.
Yeah.
And also, I guess, because if you're writing SYCL, you can also target FPGAs, which maybe some of those other models wouldn't be able to do. So yeah,
that's true. Yeah. I mean, I suppose that's the crucial thing about heterogeneous computing is theoretically you can use the processors that make the most sense for the algorithms and the code that you're running. So
yeah, exactly. And if you don't have to, bring up a whole new software suite just to target a different type of processor, then then so much the better. Obviously, you might need different algorithms and you might need to approach things slightly differently. But yeah, if you don't have to, write it in a totally different language, that's definitely a plus for productivity there.
Yeah, it definitely helps. Definitely helps. One of the other things that I noticed I think it was in December, was the SYCL hosted webinar, which I think you were part of. Well, maybe you can give us a summary of that and
Yes.
What was discussed there.
Yeah, so in December, Kronos is the organization that looks after the SYCL standard. They look after a number of other standards that you might be familiar with, obviously OpenCL, but also OpenGL and Vulkan, and they have a big set of different standards they look after, and SYCL is one of those. So in December, they hosted a webinar that was just a few hours, and that took place in December. And I hosted the event, which was nice, and we invited all of the implementers that we could get a hold of that had were able to talk about their SYCL implementations that they've been working on. So if you go to kronos.org/SYCL, there's a lovely picture there of all the different implementations that are in progress for providing SYCL, and we had most of those represented at the webinar. All the vendors provided a really fantastic update onto how they're getting on implementing SYCL 2020 in the current version of their compiler, how far they've got, what they're working on next, some top tips on how to get hold of it and how to use it. So that was really great to see that kind of status update from all those that are implementing SYCL. So as users and programmers, it's great to see, and a great source of information for getting started with those different compilers. And after that, we went into a long panel discussion where we kind of grilled all those implementers about what they thought about user questions. There was a few questions coming in from the audience. We asked them what they thought about some tricky topics, one of which was performance portability, which you'll hear a lot more about later from Vince. But yeah, it's a really great event. It was all recorded, so you can watch it after the fact, and it's all on YouTube. You can find that through the Kronos website, and also you'll find a link to that on SYCL.tech.
Cool. That sounds good. Yeah, we can include a link to that. I guess maybe the crucial question, how far away are we from implementation supporting all the SYCL 2020 features?
Yeah, I was really pleased, actually. Most of the vendors seem quite a long way towards having implemented most of the standard. SYCL 2020 was a big update on the previous version of 1.2.1. So there was a lot of new features, some changes and some clarifications, obviously, about the behavior, but just the sheer amount of features that were there. And they're all for the good. They all make our lives easier as programmers. And help us write our SYCL applications and what we can express. But it was a big change for implementers to catch up with. So I was really pleased. Lots of implementers are very nearly there with all their implementation. So I would hope over the coming few months or over this course of 2022 that we'll start to see those that will fill out and be able to say that they've supported everything.
Yeah, fantastic. Yeah. I think the team here, Compute CVP team here, have compiled a bit of a table that shows features they've implemented and progress that they're making. So that's really good. Yep. Cool. Okay. Maybe let's finish off by promoting the call for submissions at iWackle and SYCLCon, which closes on the 25th of February. So iWackle, if you go to iwackle.org is the website. So that's the annual OpenCL and SYCL conference, where there's always a lot of different, not only research papers, but also technical presentations and poster sessions, and also a few panel sessions to go with that. I know that some of my colleagues are already kind of putting together abstracts on some interesting topics. So hopefully there'll be lots of different contributions from different organizations. I guess, Tom, you've probably been quite closely involved with iWackle the last few years.
Yeah, so iWackle is chaired by a colleague in the department at Bristol, Professor Simon McIntosh-Smith. And yeah, IWOCL and SYCLCon was set up to kind of promote a kind of melting pot of people to come and talk about OpenCL and SYCL. So it's a great place for vendors and implementers of the standard and users of those different programming models, and academics and researchers that are using it, all to come together and talk about their experiences and what they'd like to see next. And it definitely does help inform the direction of both of those standards. So it's normally a great few days. Over the last couple of years, it's all been virtual, which has the benefit that all the talks are now pre-recorded and available in the archives. So you're able to catch up on the last couple of years of IWOCL talks on the website. We're expecting IWOCL to be virtual again this year. But if you're interested, as you said, the call for papers is still a few more weeks. If you're watching this close to the release, it's February, in middle of February, for the call for papers, the 25th at the moment.
Yeah, 25th. So I think the decision was made to go virtual with the conference again this year. So whilst that does mean we can't meet in person, it does mean that it doesn't matter where you are in the world, you can obviously contribute to the conference without having to worry about travel or anything like that.
Yeah, and it's not just pre-recorded. There's lots of plans for making the most of the of a time that is not too inconvenient for most people in the world, as far as possible, with all the different time zones, to make advantage of those key few hours to have some live events. So if you're interested, do keep an eye on the agenda as it gets published. And obviously, if you've got some work you've been doing that you'd like to share about OpenCL or SYCL, do think about submitting a talk or an academic paper or a poster or something to the conference.
Yeah, that sounds good. Excellent. Okay, so let's leave that for now, and we can hand over to our guest speaker, Dr. Vincent Pascuzzi. He's a physicist turned computational scientist from Brookhaven National Laboratory. He's also spent some time working in conjunction with researchers at CERN, who run experiments in the Large Hadron Collider, and I'm sure he'll go into more details about that. So let's hand over to Vincent so he can tell us more about the work he's been doing involving SYCL and what he's learned.
Okay, thanks Rod and Tom for having me. This is it should be fun. So I will talk primarily today about some of the work that I've done using SYCL in the context of performance portability, why exactly we're doing this, why it's important, and where I come from, and really drive home why it's important from my perspective. So just to start on an overview of the last 10 years or so of the evolution of the Department of Energy HPC systems, being a DOE employee at Brookhaven National Laboratory, now a computational scientist. This is, primarily the machines that we'll be utilizing. So in 2013 to 2016, you had mostly homogeneous platforms comprising CPUs of different architectures, but there's no really, back then there were no GPUs filling up a single node. Moving on to say 2018, now you have machines like Summit, and you have, say, I think 5 or 6 GPUs per node, and then Perlmutter, which is just coming online now and should be in production like mid this year. We're at 100 petaflops now, and you have, again, these heterogeneous platforms where you have a mix of CPUs and coupled with GPUs. And further on, looking, well, Aurora, hopefully we will see someday. But so again, we have Aurora, Frontier, these exascale machines that are finally coming up in the US. And again, these are highly heterogeneous. And how I categorize these is, kind of as easy and hard targets. And I'll explain a little bit why I classify it this way. So on one side, you have CPUs, which are really latency bound. And on the other side, you have like high throughput, which is GPUs, which can have hundreds to thousands of what we call simple cores generic cores. Like you can do generic calculations and branching and so forth very efficiently as you do on a CPU. But they are becoming more complex GPUs. I mean, you're having like in-core accelerators for machine learning applications, faster interconnects. You're really bringing the accelerator closer to the CPU. And then you have like, deepening memory hierarchy with cache and shared scratch pads and so on. But I think what the focus here is, mainly for CPUs, you had C++, C, Fortran, and you had a compiler for whatever architecture you had, but now you could write it in C++ or C or Fortran. Now you have, with GPUs, vendor-specific application programming interfaces, APIs, and there's no, one shoe-fits-all solution when it comes to programming these things. So if you want to target all of Aurora, Frontier, El Capitan, and so on, you need to write the same code multiple times, and you need to support it, and you need to update it and maintain it. So this becomes cumbersome, especially when you have very large experiments, very large code bases, and it's just not practical. So I mean, I won't go through all of this. This is not an exhaustive list of different programming models that can be used for heterogeneous programming, but yeah, this is just to flash everything. Of course, again, I don't include everything. So, but the goals are to have CPU latent calculations through concurrency and asynchrony. Excuse me. You want to have high levels of parallelism and heterogeneous computational throughput. For what I call the GUPM, coming from a high energy physics background, a grand unified programming model, which is to say, we're getting there. I think we have a number of, as I showed in the previous slide, programming models that have like similar goals, right? So they're heterogeneous, massive parallelism. They want to be cross-platform, of course, unless you are a vendor and you only really your first concern, of course, is your own hardware. High bandwidth memory, and then distributed, especially when it comes to like large scale workflows on exascale. Machine learning driven simulations, looking for if you're doing some studies on, say, COVID, you want to find some novel starting points to start running your simulations, which are typically computationally expensive. So beyond, also, we want classical computing. Directive-based programming models, I won't get into too much detail here. I mean, this is just an example from a previous talk that I gave, but this is just to point out, you have these pragmas that are kind of scattered throughout your code to tell the compiler which piece you want to offload, or which piece can be parallelized, and so on. But the thing to point out here is that they are portable. I mean, look at OpenMP, for example. And they're standards-based, right? So you have a standard. People that want to support this, they have to implement it inside their compilers. But with directive-based programming, I think, I mean, it's a wonderful thing. It works splendidly, of course. But this could be cumbersome having these pragmas throughout. So what the better, I think, solution overall is to have some standard C++ way to express all of your intranode parallelism. So we have like lambdas, different execution policies, which where do we want to run the code, dimensions and shapes of the data, and so on. So we have, as shown on one of the previous slides, a number of these programming models that are highly active under development. Are Cocos, Raja, Alpaca, and of course SYCL, which of course is not you have to have an implementation of SYCL. So SYCL is kind of, different here in that it's a specification, not so much an implementation of something as Cocos, where you have different implementations of SYCL as like OpenMP or MPI or something. So I think the end game here is, you may always have something like Cocos or SYCL or Raja, where, you have this exploratory base to do new and novel types of research and programming models. But eventually, a lot of these things, I think, will become of the C++ standard, and I think that's the big idea here for these different teams. C++ programming models. So yeah, I mean, if you look at the different ones like SYCL and Cocos and Raja, here I have 3 examples. They're not so different. I mean, you have explicit parallelism, your parallel patterns like your inner product or your parallel reduce. They all have a similar way of queuing or preparing your data to offload to a device, and you can handle the data either implicitly or explicitly. But I mean, aside from some syntactical differences, they can do the same job. And aside from also some performance aspects, which I don't touch on here, I mean, pick your favorite one, really. And at this point, as I said, pick your favorite one. There's no really best choice, in my opinion. I mean, you've seen a lot of use cases with Cocos and applications with Cocos, which I think it's been around for the longest time, which is what I mean by here by most mature. Raja, I think, is kind of a newer kid in the block, as SYCL perhaps as well. I mean, compared to Cocos. But SYCL has some significant industry backing. And one thing also important to note is that it's slightly lower level than other programming models, right? As I mentioned, it's a specification. It's not an implementation. It has to be implemented. So and especially if Cocos, if you want to write Cocos, a code in Cocos using Cocos and run on Intel hardware, for example, I think at this point it's almost necessary that you have SYCL support within Cocos, which they now do. Where this all comes from my perspective is I'm a high energy particle physicist by training. I worked on the ATLAS experiment for nearly a decade before becoming what we call a recovering physicist. So now I do computational science. But anyways, I still have, of course, I'm first and foremost a physicist, and my love and passion all comes from there. So this High Energy Physics Center for Computational Excellence, or HEP-CCE, is a DOE funded effort where we're looking at different parts of HPC aspects. So performance portability, input output, complex workflows, event generators, which is kind of like the first step of Monte Carlo based generation of proton collisions, or some sort of scattering experiments, cosmology. But in particular, so the other three, the top one, performance portability, is where I mostly do my work, and this is where we're focusing on looking at different programming models to give the HEP community, and maybe even more generally, some advice or suggestions on, based on their use case, which one of these programming models would be best suited for them. So what we do is we take a bunch of test beds from these 6 experiments on the top right: ATLAS, CMB, CMS, DAISY, Dune, and DESC, and we port them. And we port them to every programming model that we basically have time to or can commit to, and we evaluate them based on some criteria or characterizations. And again, why are we doing this? We have a boatload of HPC systems, new facilities coming out. We have extremely large code bases. Like I think ATLAS, for example, has like order of 1 million lines of code. So it's it's a difficult, complicated task to go through all of that code, find out which pieces are actually suitable for offloading, and then making the appropriate changes, doing the translations and the porting. But not only that, we're first and foremost physicists, so everything that we change is going to have an impact on, say, validation, and making sure that the output, regardless of which one of these machines we run on, are valid, right? I mean, think of precision measurements of say the standard model. We are very precise in what we measure, so we have to be able to replicate this in Monte Carlo, say, at a similar level of precision. And yeah, we can't afford to maintain multiple code bases, but we are also under pressure to utilize these heterogeneous platforms. And at the same time, we'd like to have a fair level of performance. So SYCL, this is, I think, if anybody's watching this meeting or interview or this blog discussion, I think knows what SYCL is. But I flashed this slide because I think it's almost mandatory in a sense. You have a number of different SYCL implementations. As I said, SYCL itself is just a specification. So you have one from Intel, DPC++, CodePlay, is actually, I'm not just saying this because Rod is here, but I actually began my studies and my work with the CodePlay Compute CPP compiler, and I never had any problems with it. I think eventually we just moved to DPC++ as, well, it was open source and it was really, under active development. Not to say that CodePlay's compiler wasn't, but I feel like a lot of people from CodePlay were also contributing to DPC++, which has been a tremendous help, especially for CUDA backend. Xilinx, SYCL is another one that I've used extensively from Heidelberg University. Axel Alplay, shout out to him. And then these other kind of newer ones, or ones I've not yet had any experience with, are NeoSYCL and Vsheng. So there's a vast ecosystem, a lot of support from different communities within industry, academia, and so on. So I feel this is a good path forward. Also potentially biased. So major features of SYCL 2020, USM, Unified Shared Memory. Again, just quickly through this, I gotta talk about some other things. Parallel reductions, workgroup and subgroup algorithms, subdevices, which are a very interesting feature in my opinion. But as of right now, I've only had any success using this on a CPU and not on a GPU, but I can understand the complications here. Atomic operations and interoperability, which is going to be highlighted later on. Single source C++ for heterogeneous applications. So this is of course stolen from Michael Wong of CodePlay. And yes, performance portability. So we take this in our work. Actually, when I say we, I mean in particular not just HepCCE, but Mehdi Gholi from CodePlay, who I believe is now the vice president of research. So kudos to Mehdi. Hopefully he's still doing real work. But yeah, we discussed performance portability in our work. Of course, we take this definition from the DOE Center of Excellence meeting, but also a more quantitative definition as given by John Pennycook of Intel and his collaborators. You can have a different criteria. Does it run? It could be a binary decision, yes or no. But you can also add some additional requirements. Does it run efficiently with respect to some baseline, which I think commonly would be the most optimal, or the native solution. Portability, can it run on multiple devices or multiple platforms, and is it adaptable to as architectures change? On the other side of the dotted line, we have productivity and reproducibility, which the latter is extremely important, I believe, or I know is extremely important in the sciences. But yeah, this is another discussion. One thing I did want to mention is, this is all great stuff, this performance portability, but I believe that it's really, it's aiming or gearing towards people as like in high energy physics, who have extremely large code bases, extremely large data that's being processed, and they need to, one HPC is just not going to cut it. And especially when you have some resources from some entity, say like the DOE, who's giving you access, or you have grants or something, you have access to these machines, and you really need to you need to process, petabytes or at least terabytes of data. But so I don't know how important, say, in general, performance portability is. I'm also ignorant to most other areas of perhaps computer science in general. But yeah, I mean, for us in particular, I just really want to emphasize the importance of performance portability. So our work started with the one API, or let me see how to say this properly, the one API, one MKL open source interfaces library, which I will refer to as OSI, okay? Because this is of course different from Intel one MKL. Hope I said that properly. So this is, developed in the SYCL programming model, part of the one API initiative, completely open source. They have functionality for linear algebra and random number generation. It's community driven, being open source. There's this technical advisory board where, we meet monthly, I think, or so, to really discuss, up and coming, what direction directions to take, what ideas people have, and it's very open. I mean, everybody is, very supportive of each other, but of course, there's an idea that's great. You go for it, but it has to be aligned with, the overall goals of the effort. And it largely relies on interoperability. For example, so interoperability, I maybe we'll say it's like, you kind of plug in third-party or existing libraries and you execute them within a SYCL application. So this has a number of benefits, and I'll talk about that a little bit later. But I mean, I think even Intel has, they don't write their own SYCL kernels, for example. And I could be wrong, but this is my belief. They have some, highly optimized, the machine code, for example, and they just call these via interoperability. They don't call the machine code directly, but they have libraries that they call via interoperability. So interoperability, I think, is an extremely useful tool. And you'll see we actually leverage this a lot in our work. So what we did was we integrated CUDA and HIP backends to target CUDA, of course, and AMD devices using 1MKL OSI. So we didn't have the resources to write a new, random number generator or fast Fourier transform library. So we took advantage of this interoperability functionality, which allows us to call, these highly optimized codes depending on what platform we're running on. There are a number of technical, hurdles that we had to overcome. We can talk about that later if you guys are interested. But basically, it was using this feature that's built into SYCL 2020 that required, very very minimal effort, to be honest with you. I mean, once you knew how to do it, it was simple. I mean, and you could do it. We did it. So we did this for CUDA and HIP. But I mean, it could be extended to ARM if there was a backend, a SYCL backend, or a compiler for ARM or any other platform. I mean, that has these libraries are readily available for you. So we have CUDA and HIP routines again. So different user controls for device selection, context, queue, and so on. 1MPI API offers the different routines. So this uses a pointer to implementation, which when you're writing an application and using this library, you use the same function calls regardless of what platform you're using. So that's kind of, simplifies a chore when you write an application, say, to run on Perlmutter, but also want to run it on Frontier. You don't have to change your code. You just have a different compiler and different underlying libraries. And then the SYCL API provides its usual things, so the data flow dependency graphs, or the DAG, dispatching kernels, and the different mappings depending on your target device. So this is mostly part of what Mehdi had done, was adding the scope handler, because there are different concepts of contexts in SYCL and CUDA. So this required some careful handling to make sure that when you're dealing with a CUDA device, for example, you had the correct context that was pertaining to the device that you were hoping to run on. And then, I think that's mostly it. It just shows some examples here of the different scopes of the application, the user application scope. So this is where you actually do write your program. And the bottom is an extension of that, showing the actual kernel submission. Here's some performance results looking at either a compute-bound case, so this is BLAST, general matrix multiplication, and on the bottom, the memory-bound AXPY. In the dark blue in each of these plots, so the left column is AXPY on two different CUDA devices. One on the top is a Tesla V100, and the bottom is a Titan RTX. And on the right is the general matrix multiply. Again, on top, the V100, and the bottom, the Titan RTX. The dark bars on these plots correspond to the native cuBLAS, and the light blue correspond to the 1MKL with the cuBLAS backend. And on the y-axis is the throughput, the gigabits per second, and on the x-axis the number of, or the size of the problem. And really, the take home here is that you have very comparable performance between the native solution which would run only on CUDA devices and the cuBLAS backend within 1MPL OSI, which can, in principle, run on any platform, any architecture. So this, I think, is a great result to show. We also did as I said, the RNG algorithms and kernels. So we implemented cuBLAS and cuRAND and HIPRAND, which, as I said, once you do one, the other one you could basically do in your sleep. So there were a couple caveats here. One being that in cuRAND and cuRAND and HIPRAND, you basically have a fixed output. So if you say I want to generate, a uniform distribution of n numbers, this is the fixed output. It's going to generate them between 0 and 1 inclusive or exclusive. I can't recall exactly, but anyhow. So we did have to do a little bit of extra work here. It's mainly implementing what we call a range transformation. So in 1MPL OSI RNG, you can specify the range of the output random numbers that you want. And so this was kind of interesting to do because this is now this range transform kernel is written purely within the SYCL programming model, which means it doesn't matter. You don't need any special libraries or anything. It can run on any architecture. And we did demonstrate this on HIPRAND, on AMD and CUDA devices. So for the benchmark applications for this work, we did our own little in-house mini app that we used to see how the scaling, how the solution scaled on different hardware. So here we generated sets of random numbers from 1 to 10 to the 8. And you might think 10 to the 8 is large, but I mean, believe me, in at least in high energy physics, that's your typical number of random numbers that you would need for processing or running Monte Carlo simulations. And we had a common code base to run on each of the different platforms, of course. And the big one here was, where this work all started was looking at the Atlas parameterized calorimeter simulation software. So this is denoted fast CaloSim. And this takes up this portion of the Atlas workflow takes up about 90% of the full workflow, as you can see in this bottom right-hand pie chart. So, and in particular, 90% of the time is spent in the electromagnetic calorimeters. And this is just due to the complexity of the physics, the geometry of the detector. When particles interact with the material, they produce additional particles, and then you have to trace and track all these additional particles that are going through the detector. Particles will stop, and energy is being deposited. So it's a complex situation, and this is the reason why it's so computationally expensive, and also why we targeted it as one of the potentials for offloading to GPUs. So here just goes through the different hardware that we use, different platforms that we use for our performance studies. We have this, we adopt this metric for performance portability, as I said, from Pennycook, and we have this. So in this formula, EI is actually our VAVS. So it's the ratio of the time to solution for whatever portability model we're looking at versus the native. Now, in principle, this should be always less than 1. The native should always be faster, or there should be a shorter time to completion or time to solution than the portable. But for some reason or another, that might not always be the case. So the mini app that we developed, so we just did what we call the RNG burner. This is the results here. So on the right, you'll see a plot on the top. This is for running on an A100 NVIDIA GPU. On the bottom, an AMD Radeon, kind of your run-of-the-mill desktop GPU. On the y-axis is the time it takes to generate what you see on the x-axis, the number of random numbers or batch size. And all across the board up until about 10 to the 5, you see basically we're not really taxing the hardware at all, I don't think, in the A100 case. And eventually, as you go up to 10 to the 6, 10 to the 7, 10 to the 8, you see this USM starting to stand out a little bit. It takes slightly longer, not, I wouldn't say an order of magnitude longer, but in any case, it's a visible difference. And this is really just due to I think the naivety of my implementation here, in that because interoperability requires like a host task. It doesn't. It's the SYCL runtime DAG is unable to handle the dependencies between the different kernels, and in order to make sure that the numbers, because we have a series of 3 kernels that run, and in order to make sure that each of these kernels that were dependent on each other would complete and have the output prepared, I was calling like wait and throw or something on the kernel launch, and this really caused some overhead, as is shown in the USM case here, which is the middle kind of violet color. On the other hand, in the Radeon on the AMD hardware, again, I don't think you can, I would take this with a grain of salt, in that the 1MKL OSI implementation of HIP brand appears to be a little faster at small batch sizes. But this could be attributed to the fact that HIP SYCL has done some serious optimizations and removed almost callbacks entirely. So for small kernels, small workloads, you can see like these optimizations really standing out. But again, once you start hitting the GPU a lot harder, you see that these numbers, these 3 different bars flatten out, and you get basically the same performance. To look at this a little bit in more depth, we looked at the different APIs, so buffer API, USM API, and then the native API. Each of the 3 kernels that are executed for a given application. So you need to seed the generator, you need to actually do the generation, and then once the generation is completed, we have this transform kernel, which gives you the desired output based on your upper and lower bounds. So we did this for the CUDA device, the A100, because we had some difficulties using the AMD profiler, and limited time, of course. But yeah, so this is a breakdown. On the top plot on the right is the execution time for each kernel on a log scale, of course. And then on the bottom is the relative occupancy in just whatever arbitrary units. And then again, on the x-axis in both cases, it's batch size. And what you're seeing here should be not impacted by the SYCL runtime at all. This is precisely showing the kernel execution time as it is running via the CUDA library. And as you see in all these cases, on the top plot, the time is, they're essentially the same. I wish I had some error bars here. But yeah, foolish to not have error bars. But you can see that each of the kernels are essentially, the runtime is exactly the same. And I mean, sure, you can assume that this should be the case, but I think anyhow, it's good to demonstrate. And then on the bottom, the relative occupancy. So for the CUDA, the native codes implementation of this mini app, we had fixed the block size to 256, and we didn't set any work group size explicitly for the SYCL implementation or the SYCL code. And you could see how this affects the relative occupancy, for example. At 10 to the from 1 to 10 to the 2, you see basically the same result for each of the different APIs. But then at 10 to the 4, because we didn't specify the workgroup size or any other properties of the kernel explicitly in the SYCL code, you see this large increase in the relative occupancy. But if you look directly above that, at the plot above it, that coincides with 10 to the 4, and for the runtime, you see that there's no change. And really, I think what's happening here is that we're asking for more compute than we're actually using, right? So the profiler is saying, oh, you asked for 10 to the 24 in terms of the block size or whatever, but really you're only using 256, so you get the same time to solution. And lastly, SYCL Sim. So this is showing on the different on two different CPUs, one AMD CPU and one Intel CPU, and then on an AMD GPU, and then on a CUDA GPU, the same two that were shown previously for the mini app. Each of so on the darker colors in the CPU case are the SYCL implementations, and on the lighter colors are the native implementations. So this is like the original code that was written by physicists in the ATLAS experiment. For the AMD case, there is no OpenCL backend for SYCL. So this is just using a host device, which I think is actually just TDB under the hood for parallelizing. And then for the Intel case, there's an OpenCL backend, and that's what we use. It's also level 0, I believe, but we use the OpenCL backend for these studies. And surprisingly, in the AMD case, using host device, it was actually slightly more performant than the native code. And the only difference here was that it's written entirely in the SYCL programming model, but also the random number generation, which wouldn't display this kind of difference in terms of the time to solution, just because the overhead for random number generation in this application is negligible compared to the overall runtime. What's nice to see though is that we had a native CUDA port, which is what we began with in this work, of SYCL Sim, which is shown on the far right, and on the top. So this is for, I should say, sorry, electrons. So single electron particles being shot into the detector at some angle, at some energy, and you can see that the SYCL port and the CUDA ports are basically again on par. And the bottom plot, you see with the T and T with a bar over top. This is the top quark, anti-top quark events, and these are much more complex. So you can have many more particles being produced as they are incident with detector material. Larger showers, so more particles going at different angles. So this requires more loading of parameters at runtime to simulate the additional particles that are produced. So you don't really get that much of a gain going to like more realistic TT bar events as you do in the single electron case. But nevertheless, I mean, you see that the take home here is that the SYCL and the native CUDA ports are both on par with each other. Not only that, but the same SYCL code was run on each of these different targets. And yeah, I think that's something to be proud about. So just to summarize, yeah, we need high performance computing. Of course, it's a driver of scientific discovery, and it doesn't come for free. So when you have access to these machines that cost you big bucks to use, you want to use them properly. We have a large number of, or a growing number of platforms, and it's not just about writing, well, at least for now, it's not just C or C++ or Fortran anymore. You have a number of different APIs that you need to use or not. We're still figuring that out. We also, in addition, or in parallel, we have a growing number of programming models, and we need to really look at these in depth and different use cases and understand which ones are best suited for a specific case over others. And not only that, I mean, what about longevity and long-term support of the programming model? Perhaps you can't put all of your eggs in one bucket or one basket, sorry. And yeah, interoperability, as we showed, is awesome. And I think that's a big push within the Kronos group and those, working on SYCL specification as well as implementation, is how to make interoperability better. As I mentioned, in the case of USM, you really use some more manual explicit control that needs to be done to ensure data dependencies are met, and this could induce some unwanted overheads. But I think a big focus should be on interoperability and improving that in different ways. And lastly, you hear people ask, is performance portability a pipe dream? And I think that's not necessarily true. You may not achieve optimal performance. But I mean, again, with interoperability, well-written code in a performance portability programming model using interoperability with, highly optimized, tuned algorithms for specific hardware, like, I think we're going somewhere, especially with the work or the motivations for getting all of this great work into the C++ standard. I think we're going to be there soon enough. So that's my talk. Thanks, guys.
Thanks, Vince. That was really fascinating, interesting hearing about the work that you've been doing. Thanks so much. Yeah, it'd be good to ask a few questions if you don't mind having a bit of a chat. I was kind of interested to hear about 1 million lines of code in the Atlas project. That's quite a lot of code to look at.
I mean, the code is only a small portion of the magnificence of this experiment.
I know, I'm sure. Yeah. I mean, how do you figure out how much of that code can be run, I suppose, in parallel on GPU type processors? I suppose you looked at one particular experiment.
There are different, I guess you can call different pieces of the code, right? I mean, I kind of touched on it. There's the first step is your Monte Carlo production, and then from there your simulation, and then from there your reconstruction. So this is taking the simulated kind of analog digital signals that are emulated and trying to convert those into physical objects or things that could be potentially represented in physical objects. You don't know for certain, because you could have some energy deposit in the detector, say, that looks to be like it could have been put there by an electron or a muon, but it takes some fancy analysis work to actually make sure with some level of certainty that is actually was a muon or an electron or whatever particle would traverse or leave that sort of signature in a detector.
Yeah. And
within each of these components, I mean, they're within simulation, it's I only talked about one portion of the calorimeter, but we have an inner detector that's made of mostly like silicon. We have around that is the calorimeter. We have different technologies used in the calorimeter, depending on the type of physics you're looking at, the electromagnetic or hadronic. And then you have the muon spectrometer that kind of wraps around everything else. So I mean, like, within like even these general components or pieces that I've laid out, there are even more. It's even more complex than that, and hence millions of lines of code in plus your analysis code. What could be parallelized? So I think the main target is right now is simulation, because this is like the most time-consuming part. Reconstruction as well, and then Monte Carlo is, I think, the Monte Carlo generation is typically a theorist area. But we do have some experimentalists, for example, within HEP-CCE, who are working on porting, these, some even Fortran code to different, like say, Cocos or SYCL. To give you a precise number of, I would say, it's hard to say. I don't think a whole lot, if that's qualitative enough. But yeah. It's hard. It's a hard question to answer.
Yeah, it's a big task. Yeah, it's quite fascinating. Yeah, cool. One of the things I was going to ask about is if you're talking about a random number generator or the FFT code that you were covering, are those able to be used by lots of different projects? Then is that the kind of idea that you can repurpose that library interface across a bunch of different experiments or simulations?
Yeah, absolutely. And anytime random number generation comes up, I'm like, hey, we have one that you can run on, X, Y, Z hardware. So yeah, that's the whole point. Is I think so we weren't out there kind of like promoting 1MKL open source interfaces at all. It was just, it just seemed like a natural fit because we were using DPC++, the libraries that are included in 1API, proper releases. And then the open source 1MKL, like originally I was, naive, goofy. I was like, oh, do you guys have random number generation here that we can use and try to run this SYCL code on different platforms? They're like, oh yeah, but it only runs on Intel because I guess interoperability, right? So they had, like, there wasn't a purely SYCL-based algorithms. They were something that was using interoperability and calling for something to target specifically Intel hardware. And then, yeah, it just kind of grew from there. But yeah, that's the idea, is that you can just, anybody who uses 1MKL proper, like can also give a shot 1MKL open source interfaces and just do it, call it in, I believe, probably the exact same way.
Cool. That's great.
Yeah, Vince, I wondered if you could talk a little bit about the productivity side of performance portability. You mentioned this a little bit on your slide, and you say you do a lot of work, rewriting codes in different programming models to explore how it went. So can you talk a little bit about that experience? What's that like? How much effort is it? And what about SYCL? How tricky was that to write?
Okay, so I will note right now that I've only really looked personally at SYCL. I mean, I work with other people. We have weekly meetings and discussions on the different programming models. But myself, I mean, primarily SYCL. I mean, I think it seems more natural than, say, a directive-based solution. Not quite as mature yet in terms of capabilities and where we could run, but coming from a C, C++, Python, background, and not being like, quote unquote computer scientist. I was doing physics. It wasn't, but I did have, interest in previous training in computer science. It wasn't an overwhelming experience. I mean, I think when this work started, it was probably late 2019 or early 2020, or even, I don't know, late 2020. I don't know, time, everything's a blur. But when I started, there was, I heard my colleague, Charles Leggett from Berkeley lab, he had said, oh, there's this nice tool called DPCT or something, or DCPT, whatever, the data parallel conversion tool.
Yeah, the code converter,
Yeah. So he was like, you should give this a shot. And I was like, okay. And then I did it. And I was like, oh my God, I have no idea what any of this stuff is. I didn't know the API. I wasn't like super familiar with SYCL at the time. And there were some caveats, like there were some, directives in the code that weren't properly translated and so forth. But I mean, that tool was a great help because it kind of gave you a side-by-side comparison. It's like, so instead of, trying to translate the entire code base all at once, I just do one file, and how does, what I know about C or C++, how does that translate into SYCL, the SYCL API? And like, that was super useful. So anybody who's new to this and DPCT, it has come a long way from what I understand. So that would be like my first, and also of course the great tutorials offered by CodePlay. And then, I don't know, what is it, SYCL.io or something? I'm sorry if I'm going off on a tangent here.
No, I know what you mean. Yeah, I think there's a website, Tech.io, that has like it's got a simple implementation running in the browser. It's only running on the host, but it means that you can kind of compile stuff and experiment and stuff like that. Yeah.
I mean, long story short, it was. I mean, if you enjoy doing something, you'll push through, right? And I think that was kind of also could have been part of it. And yeah, I mean, I was getting paid to do it, so I had to make sure it got done. But yeah, no, it was fine. I mean, it's mostly C++. It's just a new API. Right?
Yeah, but one thing I was going to ask about, I suppose, SYCL feature-wise, which you mentioned in some of the results, did you use buffers and USM yourself that much? And so how did you find the comparison between those? Because I guess I know that there are pros and cons of both, but it'd be interested to get your perspective on that.
So I think in the beginning, it was mostly buffers, and it was a little difficult just because the data structures that we were working with to use buffers. So then once USM became more mature, that just seemed like the best way to do it. Again, more work under the hood for the developer, but I mean, if you're C++ guy or person, whatever, it's very natural. It's a natural way to do it. And I think that's also probably another big push in that direction to better support USM. But use both. And I mean, buffers are all well and good, especially if you're prototyping, for example, if you're trying to get something done quickly, and then optimizations you take care of later. It's becoming a rich API, and I mean, I've done nothing super, I would say, technical. This stuff has been mostly straightforward, so I can't talk too much about the deeper parts of SYCL or any other programming model right now. But it had everything that atomic operations were important, and that came out last year or something, late 2020. So everything was there for my needs. For
the things you needed, yeah. It'd be good to, I reckon, Tom, it'd be good to try and get someone to come and do a talk about buffers and USM perhaps some point in the future.
Yeah, that'd be great.
That'd be a deep dive, perhaps.
Yeah, Vince,
in terms of performance.
Go ahead.
Go ahead, sorry.
You go.
Oh, I was just going to say, in terms of performance, they both seemed, on par. So.
Yeah, I was going to ask you about USM, and often USM is talked about as sort of a productivity feature. So if you're coming from C and C++, your memory is all allocated basically with pointers. And when you start thinking about heterogeneous programming, you have to think about sort of two things: the parallelism and getting the device to run in parallel, but then also where your data lives. Is it on the host or is it on the device? And if you're using USM, you don't have to worry about one of those things. The data will just magically move around because the hardware and the system supports that. So I just thought your perspective was interesting that that you found, and you started with buffers and accesses rather than with USM.
Yeah, but USM is like a SYCL 2020 feature.
Yeah, I mean,
right? So I started with 1.2.1, and
sure.
That kind of just as it came into DPC++, then we started leveraging it more.
Yeah.
Yeah, that makes sense.
Yeah, I wonder how, if you could then talk about the process of how tricky it was to map your original data structures in your applications to buffers and accesses. How was that process? Was there any gotchas that you wished you'd known about first, or what would you recommend people did if they were doing this too?
Structures and arrays, really just trying to keep things simple. No heavy templating. I mean, for the most part, I don't even think we wrote many classes. It was just keeping the data structures as simple as possible. And that's one of the big reasons why, taking our current code base, say in Atlas, and trying to use accelerators is complicated, because, it's very, which we've always tried to keep up with the latest C++ features and standard. So making really nice C++ code is not necessarily really nice GPU code. Nice CPU code is not necessarily, great for GPU programming. So yeah, what is it? The KISS principle: keep it simple, stupid. Don't try to over engineer, I guess. But again, this is probably not my. This is definitely not my area of expertise by any means. So somebody else would have more to say, or more enlightening thing to say here.
Yeah, I think you say that, but your results are showing that it is possible to write this kind of code that does perform well across CPUs and GPUs and using modern C++. if you take the right approach and you write the code in a way that enables that, it is possible.
For sure, yeah. You make standing on the shoulders of giants, I guess. You know, you have optimized code. Then if you can use it, then why wouldn't you?
Yep.
Cool. Okay, well, that was really interesting. Really appreciate you taking the time to come and speak to us, Vince.
Of course, this was fun.
Yeah, and hopefully we can get you back on to talk about some projects that maybe you're going to work on in the future or even currently. We'd definitely love to hear about that.
Yeah, we got some going on right now again with Mehdi. He's a great guy.
Okay, that's excellent.
So yeah, we got some other things on the go right now. Very busy time, and he's been busy. So
yeah, I'm sure.
Good, yeah.
Excellent.
It'd be great to keep in touch and keep letting us know how you're getting on with everything.
Thanks a lot, guys. Appreciate it.
Yeah, sounds good.